So there's a final kinematic equation that we can derive using the results that we just did. And so we can use our equation for the velocity as a function of time. So we can write v final is equal to v initial plus the acceleration times time. And we can use this to solve, instead of solving for anything else, we can solve for time. So what we can write this as v final minus v initial is equal to the acceleration times time. And then we can write time is equal to v final minus v initial divided by the acceleration. OK, so now I have an expression for time in terms of other quantities. Now what I'm going to do is I'm going to use the position equation that I just derived, which was x final is equal to x initial plus v initial times time plus 1/2 times the acceleration times time squared. And every place that there's a time in this equation, I'm going to insert this expression. So this is slightly algebraically messy, but it gets us to a good place in the end. So for each of these places where I have time, I'm going to insert this quantity here. So what I'm going to do is I'm going to take the value of time and substitute it in this equation. And then we'll simplify things. And this will be very useful. So I have x final minus x initial is going to be equal to v initial times the time, which is v final minus v initial divided by the acceleration, plus 1/2 times the acceleration times v final minus v initial divided by the acceleration squared. OK, so now if we simplify this a little bit, this gives us v initial times v final minus v initial squared over a plus 1/2 times a times v final squared minus 2 v final v initial plus v initial squared, all divided by a squared. So I just expanded this square here. So now you can see that this factor of a is going to cancel out. And so both of these terms are now divided by a. And so to clear this out, what I'm going to do is I'm going to multiply through by 2 and multiply through by a. And so over on this side, I'm going to get 2a times x final minus x initial. And this is going to equal, so now we have to multiply this by 2. So I have 2 v initial x v final x minus 2 v initial x squared. And over here, I have v final x squared minus 2 v final v initial x plus v initial x squared. So some nice things happen. These terms cancel out. I have a v final squared here, and I have a v initial squared and a minus 2v initial squared. So this whole thing simplifies to v final squared minus v initial squared. So this leads us directly to our third kinematic equation after all this algebra. So if I'm interested in the final velocity, I can rearrange terms here, and I can move v initial squared on the other side of this equation. And I can write v final squared is equal to v initial squared plus twice the acceleration times the displacement. So this is the last of the kinematic equations that we can derive just from these basic relationships that we've been talking about. And so this is interesting because it relates the initial and final positions and the velocities and the acceleration, but it has no time in it. So this is the only kinematic equation that we derived that is independent of time. It only relates initial and final positions and velocities. So this is sometimes useful because it allows us to shortcut some algebra. And so we occasionally will use this for doing problems.